Every second, something moves through the universe at exactly 299,792 kilometers per second. Always that speed. No exceptions. This isn't just a measured number. It's reality's speed limit, how fast anything can happen. And because nothing can break this limit, everything else has to bend instead. Our understanding of reality changed when we asked a simple question: how fast does light move? To answer that, we first need to understand what light even is. Don't forget, subscribe. Let's begin. Light is strange, stranger than most people realize. When you flip a switch and a room floods with brightness, you're not releasing some invisible fluid that fills the space. You're not turning on a continuous stream like water from a faucet. You're triggering something far weirder, a cascade of tiny, massless particles called photons, billions upon billions of them, each one behaving like both a bullet and a wave at the same time. That dual nature, particle and wave, discrete and continuous, has confused physicists for centuries. Isaac Newton thought light was made of particles, little corpuscles bouncing off surfaces. Christian Huygens disagreed. He saw light as a wave rippling through some invisible medium. They were both right. They were also both wrong. Light refuses to be just one thing. When scientists fire individual photons one at a time through two narrow slits in a barrier, something impossible happens. Each photon traveling alone somehow interferes with itself. It passes through both slits simultaneously, like a wave spreading across water. But when it hits a detector screen on the other side, it arrives as a single localized point, like a particle. One photon, two slits, both paths taken. Reality doesn't choose between wave and particle. It holds both truths in superposition until the moment of observation forces a collapse. This isn't metaphor, this is measurement. Repeatable, observable, undeniable. And it gets stranger. Light isn't just visible brightness. Visible light, the narrow band of wavelengths our eyes can detect, spanning from 400 to 700 nanometers, is a sliver of a vast electromagnetic spectrum. Radio waves with wavelengths stretching kilometers long are light. Microwaves heating your food are light. Infrared radiation you feel as warmth is light. Ultraviolet rays that burn your skin, X-rays penetrating your body, gamma rays bursting from dying stars, all light, all moving at the same speed, all obeying the same rules. The only difference: energy. Red light carries less energy per photon than blue light. Infrared carries even less. Radio waves, with their long, lazy wavelengths, carry the least. Gamma rays, tiny and violent, carry the most, enough to rip atoms apart. But despite these differences in energy and wavelength, every photon, from the gentlest radio whisper to the most destructive gamma scream, travels at exactly 299,792 kilometers per second through empty space. Why that speed? Why not faster? Why not slower? The answer lies in what photons are. They have no mass. Zero. Not very little mass. Not almost no mass. Literally none. And because they carry no mass, they experience no inertia, no resistance to acceleration. The instant a photon comes into existence, emitted from an atom released from a collision born in the heart of a star, it's already moving at full speed. It doesn't ramp up. It doesn't slow down. It just is traveling at the maximum velocity the universe permits. Other particles with mass, electrons, protons, even atoms themselves, can never reach this speed. They can get close, agonizingly close, but they can never cross the threshold. As they accelerate, they gain energy, and that energy manifests as increased mass. The faster they go, the heavier they become, the more energy required to push them even faster. To reach the speed of light would require infinite energy. The universe doesn't allow it, but photons, unburdened by mass, move at this speed effortlessly. They are the universe's couriers, carrying information, electromagnetic signals, visual data, thermal radiation, from one place to another at the fastest rate possible. Everything you see because photons left some distant object, traveled across space, and struck your retina. The stars you see at night are not as they are now. They are as they were when the light you're seeing left them years, centuries, millennia ago. Consider that every photon reaching your eye from the sun left its surface 8 minutes and 20 seconds earlier. When you look up on a clear day, you're seeing the sun as it was 8 minutes ago. If it vanished right now, blinked out of existence, you wouldn't know for another 8 minutes. For those 8 minutes, the sun would still appear in the sky, still seem to shine, even though it's gone. And this isn't unique to the Sunday. Proxima Centauri, the nearest star beyond our solar system, sits 4.3 light-years away. The photons arriving from it tonight began their journey over 4 years ago. If someone on a planet orbiting Proxima Centauri looked back at Earth with a powerful enough telescope, they'd see us as we were 4 years in the past. Our now is not their now. The concept of simultaneity, the idea that events happen at the same time across the universe, breaks down completely. The deeper implication: light doesn't just illuminate, it defines the structure of causality itself. The speed of light is the speed at which cause and effect can propagate. If something happens here, its influence, gravitational, electromagnetic, or otherwise, cannot reach a distant location faster than light can travel there. This speed sets the tempo of the universe. It determines how quickly information spreads, how fast forces act, how rapidly change unfolds. But here's the unsettling part: for centuries, no one even knew light had a speed. For most of human history, people assumed light traveled instantly. You open your eyes, you see. No delay, no journey, just immediate perception. It took a brilliant Danish astronomer staring at the moons of Jupiter to prove otherwise, and his discovery would crack open a door we're still walking through today. Aristotle thought light moved instantaneously. So did Descartes. The idea made intuitive sense. When the sun rises, it brightens the sky immediately. When you light a candle in a dark room, the walls glow without apparent delay. For thousands of years, the concept of light having a measurable speed, a journey from source to observer, seemed absurd. Galileo Galilei wasn't convinced. In the early 1600s, he devised an experiment. He stationed himself on one hilltop and an assistant on another, a few kilometers away. Each carried a covered lantern. The plan was simple: Galileo would uncover his lantern. The moment his assistant saw the flash, he'd uncover his own. Galileo would measure the time between uncovering his lantern and seeing the return signal, subtract his assistant's reaction time, and calculate the speed of light. It failed. Completely. The light appeared to travel so fast that any delay was indistinguishable from his assistant's reaction time, about 0.2 of a second. Galileo concluded only that light, if it had a finite speed, moved much faster than anything he could measure with the tools available. The breakthrough came 70 years later, not from a laboratory, but from careful observation of the night sky. Ole Rømer, a Danish astronomer working at the Paris Observatory, spent years studying Io, one of Jupiter's moons. Io orbits Jupiter every 42.5 hours, disappearing behind the planet in regular eclipses. By tracking these eclipses over months, astronomers could predict them with precision. But Rømer noticed something odd. When Earth was moving toward Jupiter in its orbit, Io's eclipses happened earlier than predicted. When Earth was moving away from Jupiter, the eclipses arrived late. The discrepancy wasn't random. It followed a pattern, shifting predictably as Earth's position changed. On November 9th, 1676, Rømer made a bold prediction. He announced that an upcoming eclipse of Io would occur 10 minutes later than the standard tables suggested. Skeptics dismissed him. The established predictions were reliable. Rømer's claim seemed reckless. The eclipse happened 10 minutes late, exactly as Rømer predicted. His explanation was elegant. Light, he argued, wasn't instantaneous. It took time to travel. When Earth was closer to Jupiter, light from Io had a shorter distance to cover, arriving sooner. When Earth was farther away, light had to travel an additional distance, roughly the diameter of Earth's orbit, which took extra time. Rømer calculated that light needed about 22 minutes to cross Earth's entire orbit. His estimate was off. The actual time is closer to 16 minutes and 40 seconds. But the principle was sound. For the first time in history, someone had proven that light had a finite, measurable speed. He estimated it at around 230,000 kilometers per second, remarkably close to the true value. Not everyone accepted it immediately. Giovanni Cassini, Rømer's superior at the Paris Observatory, rejected the idea outright. He preferred alternative explanations involving the mechanics of Jupiter's moons, but over time the evidence became undeniable. Light had a speed. It wasn't infinite. It traveled. The next leap came in the 1800s when scientists managed to measure light speed without needing astronomical distances. Armand Fizeau, a French physicist, designed an ingenious apparatus in 1849. He placed a rapidly spinning toothed wheel between a light source and a distant mirror 8 kilometers away. Light passed through a gap in the spinning wheel, traveled to the mirror, reflected back, and returned through the wheel. If the wheel rotated at just the right speed, the returning light would hit a tooth instead of a gap blocking it. By adjusting the wheel's rotation speed and measuring when the light was blocked, Fizeau calculated light speed at around 315,000 kilometers per second. Slightly high but close. Léon Foucault refined the method a few years later, using rotating mirrors instead of toothed wheels. His measurements brought the value even closer, 298,000 kilometers per second. For the first time, scientists had measured light speed in a laboratory, no telescopes or planets required. By the late 1800s, Albert Michelson pushed precision to extraordinary levels. Using interferometry, splitting light beams and recombining them to detect tiny differences in travel time, he measured light at 299,910 kilometers per second, close enough that modern instruments would need only minor corrections. In 1983, the scientific community took a radical step. They stopped trying to measure light speed more precisely and instead defined it. The speed of light in a vacuum became exactly 299,792,458 meters per second. By definition, not an approximation, not a measurement, a fixed constant used to define the meter itself. Why? Because light speed had proven so stable, so invariant, that it made a better reference point than any physical object. The meter, once defined by a metal bar in Paris, now depends on how far light travels in a fraction of a second. The speed of light isn't just a number we discovered, it's woven into the very fabric of how we measure reality. But the journey to this number revealed something deeper, something unsettling. Scientists expected light speed to change depending on the motion of the observer. After all, if you're running toward a thrown ball, it reaches you faster. If you're running away, it takes longer. Light should behave the same way, except it didn't. And that impossibility, that stubborn refusal of light to obey common sense, would shatter the foundations of physics and force us to rebuild everything we thought we knew about space-time and motion. The story of how that happened begins with one of the most famous failed experiments in history. In the late 1800s, physicists had a problem. Light was clearly a wave, it diffracted, it interfered, it behaved exactly like ripples on water. But waves need a medium. Sound waves travel through air. Ocean waves travel through water. What did light waves travel through? The answer, everyone agreed, was something called the luminiferous ether. The ether was a hypothetical substance filling all of space, invisible and intangible, yet somehow rigid enough to carry light waves at enormous speeds. It had to be everywhere, permeating the vacuum between stars, filling the space between atoms. And it had to have contradictory properties. Stiff enough to transmit light at 300,000 kilometers per second, yet thin enough that planets could pass through it without slowing down. Perfectly transparent, utterly frictionless, undetectable by any direct means. It sounded absurd. But without it, how did light travel through empty space? The ether wasn't just a convenience. It was essential to the physics of the time. If the ether existed, though, it had consequences. Earth hurtling through space at 30 kilometers per second. As it orbits, the sun should be moving through the ether like a ship cutting through water. And just as a ship experiences wind depending on its direction of travel, Earth should experience an ether wind, a detectable difference in the speed of light depending on whether it's traveling with or against Earth's motion. Albert Michelson and Edward Morley set out to measure this wind in 1887. Their apparatus was a marvel of precision. They built an interferometer, a device that splits a beam of light into two perpendicular paths, bounces them off mirrors and recombines them. If one beam traveled slightly faster or slower than the other, the recombined light would create an interference pattern visible as alternating bright and dark fringes. They mounted the entire device on a massive slab of sandstone floating in a pool of mercury to eliminate vibrations. The two light paths were perpendicular, so if Earth was moving through the ether, One beam should travel with the ether wind and the other against it, creating a measurable difference in speed. They expected a clear signal. They ran the experiment over and over, rotating the apparatus, repeating measurements at different times of day, different seasons, different orientations. They were meticulous. They were careful. They accounted for every possible source of error. They found nothing. No interference shift, no ether wind, no difference in the speed of light, regardless of direction. The light traveling parallel to Earth's motion moved at the same speed as the light traveling perpendicular to it. Exactly the same speed. It was, in the words of historians, the most famous failed experiment in physics. Failed because it didn't find what it was looking for. Famous because what it did find, or rather didn't find, was far more important. The null result was baffling. Some scientists suggested that Earth dragged the ether along with it like a planet pulling its atmosphere. But that created new problems. If the ether moved with Earth, why didn't it affect starlight passing through? Others proposed that objects contracted in the direction of motion through the ether precisely enough to cancel out any measurable effect. This explanation, called the Lorentz-Fitzgerald contraction, was mathematically elegant, but felt contrived. It was an ad hoc fix to save a theory that was crumbling. The simpler explanation, the one almost no one wanted to accept, was that the ether didn't exist at all. If there was no ether, then light didn't need a medium. It traveled through empty space on its own. And if light didn't rely on a medium, then its speed wasn't relative to anything. It was absolute. The same for all observers, regardless of motion. This violated every intuition about motion that humans had developed over millennia. If you're on a train moving at 80 kilometers per hour and you throw a ball forward at 20 kilometers per hour, the ball moves at 100 kilometers per hour relative to the ground. Velocities add. That's how motion works. But light didn't add. If you're on a spaceship moving at half the speed of light and you shine a flashlight forward, the light doesn't leave the flashlight at 1.5 times the speed of light. It leaves at exactly the speed of light, the same speed it would have if you were standing still. This constancy, this stubborn, inexplicable invariance of light's speed, was incompatible with the Newtonian mechanics that had governed physics for 2 centuries. Something had to give. And in 1905, a 26-year-old patent clerk in Switzerland named Albert Einstein figured out what. He didn't try to save the ether. He didn't propose convoluted mechanisms to explain the Michelson-Morley result. He simply accepted the experimental evidence at face value and followed it to its logical conclusion. If the speed of light is the same for all observers, he reasoned, then something else has to change. Velocities don't add the way we thought they did. Distances don't measure the way we thought they did. Time doesn't pass the way we thought it did. The ether was gone, and in its place, reality itself began to warp. Einstein's answer was so simple it seemed almost trivial. 2 short postulates, 2 assumptions about how the universe works. But from those 2 principles, everything else followed. Time slowing down, space contracting, mass increasing. The rules of reality rewritten from the ground up. And it all started with the idea that light's speed never changes. In 1905, Albert Einstein published a paper titled On the Electrodynamics of Moving Bodies. It wasn't long. It wasn't filled with complex mathematics. It didn't reference the Michelson-Morley experiment directly. It simply started with 2 ideas, 2 postulates, and worked out what had to be true if those ideas held. The first postulate: the laws of physics are the same in all inertial reference frames. That's a fancy way of saying that physics doesn't care if you're standing still or moving at a constant velocity. If you're in a train moving smoothly at 200 kilometers per hour, you can toss a ball in the air and it behaves exactly as it would if the train was stationary. You can pour water, light a candle, run an experiment, everything works the same. There's no experiment you can do inside the train that will tell you you're moving without looking outside. This wasn't new. Galileo understood it 400 years earlier. Newton built his mechanics on it. It was uncontroversial. The second postulate was the bombshell: the speed of light in a vacuum is the same for all observers, regardless of their motion. Not approximately the same. Not close enough. Exactly the same. Whether you're standing still, flying toward a light source at half the speed of light, or racing away from it at 99%. The speed of light, the light you measure, will always travel at 299,792 kilometers per second. Always. This seemed impossible. If you're on a train and someone on the platform shines a flashlight at you, common sense says the light should reach you faster than if you were standing still. But it doesn't. It reaches you at the same speed. Exactly the same. The only way both postulates could be true, the only way the laws of physics could remain consistent and the speed of light could stay constant was if space and time themselves were flexible. Here's the thought experiment Einstein used to illustrate it. You're standing on a platform. A train rushes past at close to the speed of light. Someone on the train, standing in the exact center of a car, flicks on a light. The light spreads out in all directions. For the person on the train, the light reaches the front and back walls of the car at the same time. Symmetry. Simple. But you standing on the platform see something different. The train is moving forward. By the time the light reaches the back wall has moved toward the light. By the time the light reaches the front wall has moved away from the light. The light has to travel farther to catch the front wall than it did to reach the back wall. Here's the problem: the speed of light is the same for both of you. You both measure it at exactly 299,792 kilometers per second. If the light has farther to travel to the front wall from your perspective, but it's moving at the same speed, then it must take longer to get there. But the person on the train saw the light hit both walls simultaneously. How can the light hit both walls at the same time for them, but at different times for you? The only answer: time itself is different for the two of you. The same time for the person on the train is not the same time for you on the platform. Simultaneity, the idea that two events happen at the same moment, is not absolute. It depends on your motion. There is no universal now. This was just the beginning. If simultaneity is relative, then time itself must be relative. A clock moving relative to you ticks slower than a clock at rest. Not because there's something wrong with the clock, not because of friction or mechanical wear, because time itself, the progression of moments, the flow from past to future, runs at different rates depending on velocity. And if time can stretch and compress, so can space. An object moving relative to you contracts in the direction of motion. A meter stick flying past you at 90% the speed of light isn't a meter long anymore. It's shorter, not because it's physically squished, because space itself from your perspective is compressed. These aren't illusions. They're not tricks of perception. They are measurable physical changes in the structure of spacetime. Moving clocks actually do tick slower. Moving rulers actually are shorter. Time dilation and length contraction are real. Einstein showed that space and time are not separate, independent entities. They're interwoven into a single four-dimensional fabric called spacetime. You can't change your motion through space without also changing your motion through time. The faster you move through space, the slower you move through time. The universe enforces a kind of cosmic speed limit, and it does so by warping the dimensions themselves. The equations Einstein derived, the Lorentz transformations, though he arrived at them independently, describe exactly how time dilates and space contracts depending on velocity. At everyday speeds, the effects are negligible. A car traveling at 100 kilometers per hour experiences time dilation of less than 1 part in a trillion, undetectable without atomic clocks. But at 10%, the speed of light, time slows by 0.5%. At 90%, it slows by more than half. At 99.9%, time crawls at less than 5% of its normal rate. This wasn't speculation. This was mathematics, rigorous and unavoidable, emerging directly from the two postulates. And every prediction it made, no matter how strange, turned out to be true. The implications were staggering. If time is relative, then there's no universal present, no shared now connecting all points in space. Your present is not my present. The events you consider simultaneous are not the events I consider simultaneous. The past, present, and future are not discrete, separated stages. They are perspectives dependent on motion, on velocity, on where you stand and how fast you're moving. And all of it follows from one simple fact: light's speed is constant, unchanging, absolute. But the strangest consequences weren't theoretical. They were testable. Clocks really do tick slower when they move. Time genuinely dilates. And we've measured it not just in particle accelerators or distant galaxies, but in airplanes flying around the Earth, in satellites orbiting overhead, even in particles raining down from the upper atmosphere. The evidence is everywhere, and it's undeniable. In 1971, two physicists named Joseph Hafele and Richard Keating did something unusual. They bought tickets on commercial airline flights, regular passenger jets, and brought along some of the most precise timekeeping devices ever built, cesium atomic clocks. They flew east around the world. Then they flew west. The entire time the atomic clocks ticked, counting every billionth of a second with extraordinary accuracy. When they returned and compared the clocks to identical ones that had stayed on the ground, they found something remarkable. The traveling clocks had aged differently. Not by much, just a few hundred nanoseconds, a few hundred billionths of a second. But the difference was there, measurable, real. The eastbound clock flying in the direction of Earth's rotation had lost time compared to the ground clock. The westbound clock flying against Earth's rotation had gained time. The discrepancies matched Einstein's predictions almost exactly. Time moving at different velocities had passed at different rates. This wasn't a trick. It wasn't experimental error. It was time dilation proven with atomic clocks on passenger jets. The effect is small, at airplane speeds a few hundred kilometers per hour, but it's not zero. And when things move faster, the effect grows. A lot faster. High in Earth's atmosphere, cosmic rays, high-energy particles from space, smash into atoms in the air. These collisions create showers of secondary particles, including something called muons. Muons are unstable. They decay rapidly, with a half-life of just 2.2 microseconds, 2.2 millionths of a second. That's how long on average a muon exists before it disintegrates into other particles. At 99% the speed of light, a muon should travel about 600 meters before decaying. The upper atmosphere where muons are created is about 15 to 20 kilometers above the ground. By all rights, muons shouldn't make it to the surface. They should decay long before reaching sea level. But they do, in huge numbers. Muons are detected constantly, at ground level, far below where they should have disintegrated. The reason: time dilation. From our perspective, watching the muons streak downward at near light speed, their internal clocks run slow. What feels like 2.2 microseconds to the muon stretches to 20 or 30 microseconds from our frame of reference. That extra time, that dilation, gives them enough life to reach the ground. From the muon's perspective, though, something different happens. To the muon, time passes normally, but the distance it has to travel, the 20 kilometers of atmosphere, is contracted. Compressed, the muon doesn't see itself living longer. It sees the atmosphere as thinner, the journey as shorter. Both perspectives are correct. Both are real. This is what relativity means. Reality depends on your frame of reference. Time and space are not fixed stages on which events unfold. They warp, they flex, they adjust to keep the speed of light constant, and the consequences can be dramatic. There's a famous thought experiment called the twin paradox. One twin stays on Earth, the other boards a spaceship and travels to a star 10 light-years away at 90% the speed of light. The trip takes about 11 years each way for a total of 22 years. When the traveling twin returns, she expects her Earth-bound sibling to have aged 22 years. But he hasn't. He's aged more than 46 years. The traveling twin, moving at high speed, experienced time more slowly. For her, the journey felt like 22 years. For him, waiting on Earth, it was more than 4 decades. She's younger, significantly younger. Not because of biology, because of physics. This isn't hypothetical anymore. NASA conducted a real version of this experiment, though on a much smaller scale, with astronauts Scott and Mark Kelly, identical twins. Scott spent 340 days aboard the International Space Station, orbiting Earth at about 28,000 kilometers per hour. Mark stayed on the ground. When Scott returned, scientists compared their biological markers. Scott's telomeres, the protective caps on chromosomes that shorten with age, had lengthened slightly during his time in space, likely due to the stress of microgravity and radiation. But his chronological age, measured by atomic clocks, had changed by a different amount. Scott aged about 13 milliseconds less than Mark. 13 thousandths of a second. Tiny, but measurable. Confirmed. Scott Kelly, having moved faster, experienced slightly less time. The effect would be far more pronounced at higher speeds. If Scott had traveled at 99% the speed of light for a year, he would have returned to find Mark decades older. The universe enforces this without exception. Time is not a universal constant. It's a variable dependent on velocity. The faster you move through space, the slower you move through time. Always, no matter what. GPS satellites experience this constantly. They orbit at about 20,000 kilometers above Earth, traveling at roughly 14,000 kilometers per hour. Relativity affects them in two opposing ways. First, because their moving special relativity says their clocks should tick slower than clocks on the ground, about 7 microseconds per day slower. Second, because they're farther from Earth's gravitational pull, general relativity says their clocks should tick faster, about 45 microseconds per day faster. The gravitational effect dominates, so GPS satellite clocks run about 38 microseconds per day faster than clocks on Earth. 38 microseconds doesn't sound like much, but GPS works by measuring the time it takes for signals to travel from satellites to receivers. Light travels about 300 meters per microsecond. If you don't correct for the time dilation, GPS positions drift by about 11 kilometers per day. Within hours, the system would be useless. So, engineers adjust the satellite clocks before launch. They set them to tick at a slightly slower rate, 10.2299999954. 3 MHz instead of the standard 10.23 MHz. Once in orbit, time dilation and gravitational effects bring the clocks into sync with ground-based time. Relativity isn't just a theoretical curiosity. It's a practical necessity baked into the technology you use every day. And it's not just clocks. Particle accelerators like the Large Hadron Collider routinely accelerate protons to 99.999991%, the speed of light. At that speed, time dilation increases the proton's effective lifespan by a factor of more than 7,000. Particles that would normally decay in fractions of a second survive long enough to complete millions of laps around the 27-kilometer ring. Every one of these phenomena, Hafele-Keating's clocks, atmospheric muons, aging astronauts, GPS satellites, particle accelerators, confirms the same thing. Time dilates. It slows when you move. The faster the motion, the greater the effect. And it's not an approximation. It's precise, predictable, measurable. Time, the thing we experience as constant and universal, the thing that seems to flow smoothly from past to future, is flexible. Relative, dependent on motion. But time isn't the only thing that warps. Space itself contracts when objects move, squeezing distances along the direction of motion. And more disturbing still, the very concept of now, the idea that events happen simultaneously across the universe, dissolves completely. What you consider now is not what someone else moving differently considers now. The universe has no shared present. Time bends. That much is clear. But time doesn't bend alone. If time dilates for an object in motion, space must contract. They're two sides of the same phenomenon, two faces of a unified four-dimensional spacetime. And just as moving clocks tick slower, moving rulers shrink. Length contraction is harder to visualize than time dilation, but it's just as real. An object moving relative to you becomes shorter in the direction of its motion. Not compressed like a sponge squeezed in your hand. Not physically crushed. Just shorter. From your perspective, a spaceship 100 meters long, measured while at rest, shrinks when it accelerates. At 50% the speed of light, it's about 87 meters long from your perspective. At 90%, it's about 44 meters. At 99.9%, it's less than 4.5 meters. The faster it goes, the shorter it becomes. But here's the critical part the people inside the spaceship don't notice. To them, the ship is still 100 meters long. Their rulers haven't shrunk. Their perceptions haven't changed. What has changed is space itself as measured between reference frames. This creates strange scenarios. The Large Hadron Collider accelerates protons to 99.9999991%, the speed of light. At that speed, the protons don't experience the 27-kilometer ring as 27 kilometers. From the proton's perspective, the distance around the ring is contracted down to just a few meters. The protons whip around what feels to them like a tiny loop, while from the lab's perspective, they're circling a massive underground tunnel. Both views are correct, and this applies to everything. Galaxies, moving away from us at high velocities, are contracted in the direction of their motion. Cosmic rays streaking through the atmosphere experience the thickness of the air as paper thin. Distances are not absolute. They depend on motion, but the strangest consequence of relativity isn't time dilation or length contraction. It's the loss of simultaneity. In Newtonian physics, simultaneity was simple. If two events happened at the same time, they happened at the same time for everyone. You could synchronize clocks across the universe, and they'd all agree on when now was. Relativity destroys this. Two events that are simultaneous in one reference frame are not simultaneous in another. The order of events can even reverse depending on your motion, though only for events that are causally disconnected, events that can't influence each other. Here's an example. Two firecrackers explode 1 kilometer apart. You're standing exactly in the middle. The light from both explosions reaches you at the same time. You conclude the firecrackers exploded simultaneously. But someone running toward one firecracker and away from the other sees something different. Because they're moving the light from the firecracker, they're running toward reaches them first. From their perspective, that firecracker exploded earlier. There's no objective answer to which firecracker exploded first. The question itself is meaningless. Simultaneity is not a property of events. It's a relationship between events and observers. Your now is not my now. This has profound implications. It means there's no universal present moment, no cosmic now slicing through space-time, separating past from future for the entire universe. The present is local, personal, tied to your state of motion. If you're sitting still and someone across the galaxy is also sitting still relative to you, you might agree on simultaneity. But if they're moving even slightly, your definition of now diverges from theirs. Events you consider to be happening right now at this instant are events they consider to be in the past or future. Extend this to the entire universe, and the picture becomes even stranger. Every observer, every galaxy, every particle has its own definition of now. The universe doesn't have a single timeline. It has as many timelines as there are perspectives. This is why physicists talk about spacetime as a block. Past, present, and future don't flow from one to the next. They all exist, laid out in a four-dimensional structure. You're not moving through time from past to future. You're a four-dimensional object stretched across time, experiencing different slices of your existence sequentially. From this view, the past isn't gone. It's just a region of space-time you're no longer intersecting. The future isn't unwritten. It's just a region you haven't intersected yet. Everything that has happened, is happening, or will happen, is already there embedded in the structure of spacetime. Einstein himself believed this. When his lifelong friend Michele Besso died in 1955, Einstein wrote to Besso's family, "Michele has left this strange world a little ahead of me. That means nothing." For us, believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion. An illusion. Not because time doesn't exist, but because the flow of time, the sensation of moving from past to future, is a perspective, not an objective feature of the universe. This is deeply unsettling. It challenges our intuition about free will, causality, the nature of existence itself. If the future is already there, laid out in space-time, do our choices matter? Are we discovering the future or creating it? Relativity doesn't answer these questions. It simply shows that the common-sense notion of time universal, flowing dividing past from future for everyone, is wrong. Time is weirder than we thought. More flexible, more dependent on context. And all of this emerges from a single fact: the speed of light is constant. But constancy has a price. If light speed can't change, then something else must give when you try to accelerate. And that something is mass. The faster you go, the heavier you become. Not just harder to push, actually physically heavier. And if you tried to reach the speed of light, your mass would become infinite. The universe doesn't allow it. The question is why? In the same year, Einstein published his theory of special relativity 1905. He published another short paper. This one was only 3 pages long. It introduced an equation so simple, so elegant, that it's become the most famous equation in history. E equals mc squared. Energy equals mass times the speed of light squared. It looks almost trivial. But what it says is staggering mass and energy are the same thing. Not similar, not related, the same. Mass is congealed energy. Energy is liberated mass. They're two forms of the same substance. A single gram of matter, less than the weight of a paperclip, contains about 90 trillion joules of energy. That's the energy released by the atomic bomb dropped on Hiroshima, all from 1 gram. The speed of light squared, about 9 times 10 to the 16th meters squared per second squared, is an enormous conversion factor. Even a tiny amount of mass represents a colossal amount of energy. This is why stars shine. Every second, the sun converts about 4 million tons of mass into pure energy through nuclear fusion. 4 million tons. Just gone. Transformed into light and heat. And that's every second. Over billions of years, the sun has burned through a significant fraction of its original mass, but it's so massive, about 2 times 10 to the 30 kilograms, that it can sustain this for billions of years more. This is also why atomic bombs work. When uranium or plutonium undergoes fission, a tiny fraction of the atomic nucleus's mass, about 0.1%, converts to energy. That's all it takes. Less than 1%. The result is devastation, but the equation has another consequence, one that explains why nothing with mass can reach the speed of light. As an object accelerates, you're adding energy to it. In Newtonian mechanics, that energy becomes kinetic energy, the energy of motion. The faster the object moves, the more kinetic energy it has. Simple. But in relativity, adding energy doesn't just increase speed indefinitely. At high velocities, the added energy also increases the object's mass. Not its rest mass, the mass it has when stationary, but its relativistic mass, the effective mass it has when moving. The faster you go, the heavier you get. And the heavier you get, the more energy it takes to accelerate you further. At low speeds, the effect is negligible. A car moving at 100 kilometers per hour has a relativistic mass increase of about 1 part in 100 trillion. Undetectable. But as you approach the speed of light, the effect explodes. At 10% the speed of light, your mass increases by about 0.5%. At 50%, it increases by about 15%. At 90%, it more than doubles. At 99%, it increases by a factor of 7. At 99.999% by a factor of more than 200. And as your mass increases, the energy required to accelerate you increases too. To go from 99% to 99.9%, the speed of light requires far more energy than going from 0 to 99%. Every increment closer to light speed demands exponentially more energy. At exactly the speed of light, your mass would become infinite. And accelerating infinite mass would require infinite energy. The universe doesn't have infinite energy, so nothing with mass can reach light speed. Ever. This isn't a technological limitation. It's not that we haven't built powerful enough engines yet. It's a fundamental law of physics. The speed of light is a barrier woven into the structure of spacetime itself. Only massless particles, photons, and possibly gravitons can travel at this speed, and they do so effortlessly because they have no mass to increase. Particle accelerators demonstrate this limit constantly. The Large Hadron Collider accelerates protons to 99.9999991%. The speed of light 7 nines. At that speed, the protons have about 7,000 times their rest mass. They're incredibly heavy, relativistically speaking. To push them to 99.9999999%, 8 nines would require doubling the energy again. To reach exactly the speed of light would require infinite energy. The LHC can't do it. Nothing can. But that's not a failure. It's a feature. The speed of light isn't just a speed limit. It's the speed at which causality itself propagates. It's the maximum rate at which any information can travel through space. If you could exceed the speed of light, you could send a signal backward in time. You could receive a reply before you sent the message. Cause and effect would become tangled. Paradoxes would emerge. The structure of reality would break down. The universe prevents this by making light speed unreachable for anything with mass. The closer you get, the harder it becomes. The barrier is absolute, but even without reaching light speed, the energy-mass relationship has transformed technology. Positron emission tomography PET scans relies on antimatter. When a positron encounters an electron, they annihilate, converting their combined mass entirely into energy. Two gamma rays shoot out in opposite directions. Medical scanners detect those gamma rays and use them to map metabolic activity in the brain, heart, and other organs. It's E equals mc squared turned into a diagnostic tool. Nuclear reactors work the same way. A small amount of mass converts to energy-producing heat that boils water, drives turbines, generates electricity. The efficiency is extraordinary. 1 kilogram of uranium fully converted could power a city for days. In practice, only a fraction of a percent converts, but even that fraction releases enormous energy. And in the depths of space, particle collisions at near light speeds create new particles out of pure energy. When protons smash together in the LHC at 13 trillion electron volts, the kinetic energy converts into matter quarks, gluons, Higgs, bosons particles that didn't exist before the collision. Energy becomes mass. The equation runs both ways. This is the universe we live in. Mass and energy are interchangeable. Motion warps space-time. The speed of light is a cosmic constant, a boundary nothing can cross. And all of it follows from those two simple postulates. Einstein started with physics is the same in all inertial frames, and the speed of light is the same for all observers. Everything else, time dilation, length, contraction, mass, increase the equivalence of mass and energy is consequence. Unavoidable, proven, real, rehook to destination 8. These aren't just abstract principles anymore. They're embedded in the technology we use daily. GPS navigation, medical imaging, particle physics, all of them depend on relativity. Without understanding how time bends and space contracts, none of these tools would work. The universe's strange rules have become our tools, and they work because those rules are true. Relativity sounds abstract. Time slowing down, space compressing, mass increasing. These effects seem impossibly distant from ordinary life, relevant only in particle accelerators or science fiction. But relativity is not academic. It's practical. It's woven into the technology you use every day. GPS, the Global Positioning System, is the most direct example. Every time you open a map app on your phone, check your location, or navigate to an address, you're relying on Einstein's equations. GPS works by triangulating signals from satellites. At least 4 satellites beam timing signals to your receiver. The receiver calculates how long each signal took to arrive, determines the distance to each satellite, and pinpoints your position. Precision matters. Light travels about 30 centimeters per nanosecond, 1/1000th of a second. An error of 10 nanoseconds translates to a 3-meter error in position. If the timing is off by microseconds, GPS becomes useless. And timing is off constantly. Because the satellites are moving and because they're in a weaker gravitational field than you are, time runs differently for them than it does for you. Special relativity says that because the satellites are moving at about 14,000 kilometers per hour, their clocks should tick slower than clocks on the ground, about 7 microseconds per day slower. But general relativity says that because the satellites are 20,000 kilometers above Earth's surface, farther from the planet's gravitational pull, their clocks should tick faster, about 45 microseconds per day, faster. The gravitational effect dominates. Net result, satellite clocks run 38 microseconds per day faster than ground clocks. 38 microseconds per day means roughly 11 kilometers of error per day. After just a few hours, GPS would tell you you're blocks away from your actual position. After a day, it would be off by kilometers. Engineers correct for this before the satellites even launch. The atomic clocks on board are set to tick at a frequency slightly slower than the standard 10.23 MHz, specifically 10.22999999543 MHz. Once in orbit, the relativistic effects bring the clocks into synchronization with ground time. This isn't a one-time calibration. GPS satellites constantly adjust, accounting for variations in orbit, gravitational fields, velocity changes. Relativity isn't a footnote in the system's design. It's central to how GPS works. Without it, the system would fail within minutes. So every time you check your location, you're confirming Einstein's predictions. Your phone is a laboratory running experiments in space-time geometry, proving that time bends with gravity and motion. And it works. Flawlessly. PET scans, positron emission tomography, take relativity even further. These medical imaging devices use antimatter. A patient is injected with a radioactive tracer, typically a sugar molecule tagged with fluorine-18, an isotope that decays by emitting positrons. Positrons are the antimatter counterparts of electrons. When a positron encounters an electron, and it will almost immediately, because electrons are everywhere, they annihilate. Their combined mass converts entirely to energy, exactly as E equals mc squared predicts. The annihilation produces two gamma rays, shooting out in opposite directions at exactly 180 degrees apart. The PET scanner detects these gamma rays and uses their trajectories to pinpoint where the annihilation happened, which reveals where the radioactive tracer is concentrated in the body. Cancer cells, which metabolize sugar, rapidly absorb more tracer and glow brightly on PET scans. Brain regions with high activity light up. Hearts struggling to pump blood show dim patches where tissue isn't getting enough oxygen. This is mass energy conversion turned into medicine. Without E equals mc squared, PET scans wouldn't exist. And without PET scans, diagnosing cancer, monitoring brain function, and assessing heart disease would be far more difficult. Particle accelerators are another domain where relativity isn't optional. At CERN, the Large Hadron Collider accelerates protons to 99.9999991%. The speed of light so close to light speed that the difference is almost negligible. At that velocity, protons complete about 11,245 laps around the 27-kilometer ring every second. But from the proton's perspective, time is massively dilated. The proton's internal clock runs so slowly that what feels like a fraction of a second to the proton corresponds to minutes in the lab. And because of length contraction, the proton doesn't see the 27-kilometer ring as 27 kilometers. It sees a tiny loop compressed down to just meters in the direction of motion. When these protons collide, their kinetic energy, the energy of motion, converts into mass. New particles materialize: quarks, gluons, W and Z bosons, sometimes even Higgs bosons. These particles didn't exist before the collision. They were created from pure energy. This is how physicists discovered the Higgs boson in 2012. They smashed protons together at such high energies that the collisions created Higgs particles, which decayed almost instantly into other particles that detectors could measure. Energy became mass, relativity in action. And it's not just high-energy physics. Relativity affects chemistry too. Gold, for instance, is gold-colored because of relativity. Most metals reflect light evenly and appear silver or gray. Gold absorbs blue light and reflects yellow because its electrons move so fast, close to half the speed of light, that relativistic effects alter their energy levels. Without relativity, gold would look like silver. Mercury is liquid at room temperature, partly because of relativistic effects on its electron shells, which weaken the bonds between atoms. Lead's density, bismuth's diamagnetism, the stability of certain heavy elements, all influenced by relativity. Even the magnets on your refrigerator work partly because of relativity. Magnetism arises from moving electric charges, and at the quantum level, the interaction between electric and magnetic fields is inherently relativistic. The equations describing electromagnetism, Maxwell's equations, are already consistent with special relativity. Einstein didn't invent relativity to fix those equations. He derived relativity from them. In other words, relativity was hiding in plain sight all along, embedded in the structure of electromagnetism, waiting for someone to notice that the speed of light wasn't just a measured constant but a fundamental limit. All of this GPS PET scans particle colliders the color of gold. The liquidity of Mercury depends on the same core principles. Time dilates, space contracts, mass and energy interchange, and the speed of light remains constant no matter what. These aren't curiosities. They're the rules that govern how the universe operates, from the smallest subatomic scales to the largest cosmic distances. And we've learned to use them, to harness them, to build tools that wouldn't function without them. Relativity isn't exotic anymore. It's mundane, everyday, invisible but essential. And yet, for all its presence in technology, relativity imposes a harsh limit on what we can do. The speed of light isn't just a number. It's a boundary isolating us in space-time. It determines how far we can reach, how fast we can communicate, how much of the universe we can ever hope to touch. And that limit is absolute. Light moves fast enough to circle Earth 7.5 times in 1 second. Fast enough to cross the distance from the Moon to Earth in just over 1 second. Fast enough that for most of human history it seemed instantaneous. But the universe is vast, and even at light speed, distances become gulfs, barriers, walls of time that cannot be crossed. The sun is 8 light minutes away. 8 minutes and 20 seconds to be precise. When you see the sun in the sky, you're seeing it as it was 8 minutes ago. If it suddenly vanished, went dark, ceased to exist, you wouldn't know for 8 minutes. For those 8 minutes, you'd still see it shining, still feel its warmth, still live in a world where the sun existed even though it didn't. Mars, at its closest approach to Earth, is about 3 light minutes away. At its farthest, about 22 light minutes. When NASA sends a command to a rover on Mars, it takes between 3 and 22 minutes to arrive. The rover's response takes just as long to come back. A simple question and answer exchange can take nearly an hour. Proxima Centauri, the nearest star beyond the Sun, sits 4.3 light years away. A message sent there would take 4.3 years to arrive. A reply would take another 4.3 years to return. 8.6 years minimum for a conversation. One question, one answer. If we discovered a planet orbiting Proxima Centauri, and if we detected signs of intelligent life there, and if we sent a greeting, we'd wait nearly 9 years for any possible response. By the time we heard back, the political leaders who authorized the message might be out of office. The scientists who sent it might be retired. The world might have changed, and Proxima Centauri is close. Cosmically speaking, it's in our neighborhood. The Milky Way galaxy, just our galaxy, is about 100,000 light years across. A signal sent from one edge would take 100,000 years to reach the other. The Milky Way contains somewhere between 100 billion and 400 billion stars. Most of them are thousands, tens of thousands, hundreds of thousands of light years away. If any of those stars host civilizations, we are separated from them by millennia of travel time. At light speed, and nothing travels faster than light. The Andromeda Galaxy, our nearest large galactic neighbor, is 2.5 million light years away. The light reaching Earth from Andromeda tonight left that galaxy 2.5 million years ago, long before humans existed. When you look at Andromeda, you're seeing it as it was in the deep past. You have no idea what it looks like now. You can't. The information hasn't arrived yet. If someone in Andromeda is looking back at Earth with an impossibly powerful telescope, they're seeing Earth as it was 2.5 million years ago. Early hominids, no cities, no technology, no sign of intelligence, our now and their now are separated by millions of years of light travel. This creates a profound isolation. We can see distant galaxies, billions of them scattered across billions of light years, but we see them only as they were in the past. Some of the galaxies visible in deep space images no longer exist. They've collided, merged, been torn apart by gravitational forces. But because they're so far away, their light is still traveling toward us, carrying images of a universe that has already changed. The James Webb Space Telescope, launched in 2021, has observed galaxies more than 13 billion light-years away. These galaxies formed when the universe was only a few 100 million years old, just 3% of its current age. The light from them has been traveling for over 13 billion years. What those galaxies look like now, whether they still exist, what they've become, is unknowable. We can't see their present. We can only see their ancient past. The observable universe, the sphere of space from which light has had time to reach us, has a radius of about 46 billion light-years. That's larger than 13.8 billion light years, the age of the universe, because space itself has been expanding while light travels through it. But 46 billion light years is still a limit. Beyond that boundary, light hasn't had time to reach us. Anything farther away is invisible, not because it doesn't exist, because its light hasn't arrived yet. And if the universe's expansion continues, accelerating, some of that light never will. There are regions of space receding from us faster than light can close the gap. Not because they're moving through space faster than light, nothing does that, but because space itself is expanding between us. Galaxies far enough away are being carried beyond our cosmic horizon. We'll never see them, never contact them, never know what's there. This is the loneliness the speed of light imposes. We are embedded in a universe teeming with galaxies, stars, perhaps civilizations, but we can only ever interact with a fraction of it. Most of the universe is beyond our reach, hidden behind barriers of distance and time. Even within the reachable universe, communication is slow. If we detect a signal from a civilization 1,000 light years away and we send a reply, the conversation will span 2,000 years. Civilizations rise and fall in less time. Languages evolve. Cultures transform. By the time our reply arrives, the senders might be gone. By the time we hear back, we might be gone. And travel. Even worse. The fastest spacecraft humans have built, the Parker Solar Probe, travels at about 190 kilometers per second, fast enough to cross the United States in less than a minute. But that's only 0.06% the speed of light. At that speed, reaching Proxima Centauri would take over 6,000 years. Reaching the center of the Milky Way would take millions of years. Even if we could build a ship capable of traveling at 10% the speed of light, far beyond current technology, a trip to Proxima Centauri would take 43 years. The travelers who left Earth would arrive middle-aged or elderly, and Earth would have changed. Everyone they knew would be older. Some would be dead. The world they returned to, if they returned, wouldn't be the one they left. At 90%, the speed of light, time dilation would compress the journey from the traveler's perspective. A trip to a star 10 light years away might feel like only a few years to them, but when they returned, 20 years would have passed on Earth. Their friends, their families, everyone they knew would have aged 2 decades. They'd step off the ship into a future. This is the price of relativistic travel. You trade your present for someone else's future. You become unstuck from the shared timeline of your home, and there's no going back. Time doesn't run backward. You can't undo the dilation. And all of this assumes we could build ships capable of relativistic speeds. We can't. Not yet. Not even close. The energy required to accelerate a spacecraft to even a small fraction of light speed is enormous. The fuel, the propulsion, the shielding against interstellar radiation, all of it is beyond our current capability. The speed of light is a cage, not because it's slow, but because the universe is so incomprehensibly vast. Distances that sound small in light years translate to journeys that span lifetimes, generations, centuries. We are in a very real sense alone, isolated by the speed at which information can travel, surrounded by a universe we can see but cannot touch. But perhaps that isolation isn't a flaw. Perhaps it's by design. The speed of light doesn't just limit travel, it defines causality. It ensures that cause and effect unfold in order that information can't arrive before it's sent, that the universe remains coherent, and if time and space are truly woven into a single unchanging structure. A block universe, where past, present, and future all exist at once. Then perhaps our isolation is the price we pay for a reality that makes sense. Einstein didn't just change how we think about motion and light, he changed how we think about time itself. In Newtonian physics, time was a universal river flowing at the same rate everywhere. The past was gone. The future hadn't happened yet. Only the present, the now, was real. You could synchronize clocks across the universe, and everyone would agree on when things happened. Relativity destroys that picture. Time is not universal. It's not a river. It doesn't flow at the same rate everywhere. Two observers moving at different velocities experience different rates of time passage. Events that are simultaneous for one observer are not simultaneous for another. There is no shared now. This leads to a strange conclusion. Maybe the distinction between past, present, and future is an illusion. Maybe all moments, everything that has ever happened, is happening or will happen, exist equally, not sequentially, not flowing from one to the next. Just existing all at once, laid out in a four-dimensional structure called the block universe. From this perspective, time is like space. You don't move through space. You exist at a location in space. Similarly, you don't move through time. You exist at a location in time. Your entire life, from birth to death, is a static structure, a four-dimensional world line stretching through space-time. Different moments of your life are different slices of that world line. Right now, you're experiencing one slice. A moment ago, you were experiencing a different slice. A moment from now, you'll experience another. But all those slices exist simultaneously. They're all equally real. The past isn't gone. It's just a slice you're no longer experiencing. The future isn't unwritten. It's just a slice you haven't experienced yet. This is deeply counterintuitive. It feels like time flows, like the present is real and the past is gone and the future is open. But feelings don't dictate reality, and the mathematics of relativity suggests otherwise. Consider two events separated by space. One happens here, one happens on a distant planet. Whether those events are simultaneous depends on your motion. If you're at rest relative to both, you might say they happen at the same time, but if you're moving, you'll measure them as happening at different times. One observer's now is another observer's past or future. If simultaneity is relative, then now is relative. And if now is relative, there's no universal present moment slicing through the universe, separating what has happened from what hasn't. The entire history of the universe, past, present, future, must already exist in some sense. Otherwise, what does it mean for an event to be in your past, but someone else's future? Einstein believed this. When his lifelong friend Michele Besso died in 1955, Einstein wrote a letter to Besso's family. In it he said, "Now he has departed from this strange world a little ahead of me. That means nothing. People like us, who believe in physics, know that the distinction between past, present, and future is only a stubbornly persistent illusion. An illusion, not because time doesn't exist, but because the flow of time, the sense that the present is uniquely real, is a feature of consciousness, not a feature of the universe. But if the block universe is real, what does that mean for free will? If the future already exists, laid out in space-time, are our choices predetermined? Are we just moving along pre-existing world lines, discovering a future that's already written? Relativity doesn't answer this. It only shows that the structure of space-time is fixed. The past, present, and future are all part of that structure. But whether that implies determinism, whether the future is fixed in a causal sense, is a separate question. Physics doesn't forbid free will. It just changes what free will might mean. One interpretation is compatibilism. Your choices are part of the structure. You make decisions, and those decisions shape your world line. The fact that the world line exists as a four-dimensional object doesn't mean you didn't make the choices. It just means those choices are embedded in space-time, not separate from it. Another interpretation is that consciousness creates the illusion of flow. You experience time sequentially because your brain processes information sequentially. Memories form in the past. Anticipation looks toward the future. But the underlying reality is static. You're not moving through time. You're a static pattern in space-time, and different parts of that pattern experience themselves as existing at different moments. This is where physics ends and philosophy begins. Relativity tells us what the structure of space-time is. It doesn't tell us what it means to exist within that structure. But there's one more consequence of light's constant speed, the speed of causality. Causality, the principle that causes precede effects, is fundamental to how we understand the universe. You can't have an effect without a cause, and the cause must happen before the effect. Otherwise, logic breaks down. The speed of light enforces this. Information cannot travel faster than light. Cause and effect propagate at light speed or slower. If you do something here, its influence can't reach a distant location faster than a light signal could travel there. This means that events separated by distances greater than light can travel in a given time are causally disconnected. They can't influence each other. One can't cause the other. And this is why faster than light travel creates paradoxes. If you could send a signal faster than light, you could send it backward in time from the perspective of some observers. You could receive a response before you sent the message. Cause would follow effect. The structure of space-time would unravel. The universe prevents this by making light speed an absolute barrier, not just for matter but for information, for causality, for the very notion of cause and effect. The speed of light is the speed at which reality propagates. It's the maximum rate at which anything, matter, energy, information, influence, can move through space-time. And that limit isn't arbitrary. It's built into the geometry of the universe itself. From a certain perspective, light doesn't even experience time. Photons travel at light speed, and at light speed, time dilation is infinite. From a photon's perspective, the journey from a distant star to your eye takes zero time. It's emitted and absorbed in the same instant from its frame of reference. It doesn't age. It doesn't experience duration. It just is connecting 2 points in space-time with no subjective passage of time in between. This is the universe we live in, a four-dimensional block where past, present, and future coexist, where time is relative dependent on motion, where the flow of moments is a feature of consciousness, not an objective property of reality, where the speed of light sets the tempo of causality, the maximum rate at which anything can happen, and where we embedded in this structure experience time sequentially moving from one moment to the next, discovering a future that may already exist. Einstein saw this. He accepted it. He lived with the discomfort of a universe where time is not what it seems. The distinction between past, present, and future, he wrote, is only a stubbornly persistent illusion. Perhaps he was right. Perhaps the flow of time is something our brains create, a narrative we tell ourselves to make sense of existence. Perhaps the universe doesn't flow at all. It simply is. And light traveling at its fixed, unwavering speed is the thread that stitches it all together. The speed of light is not just a measurement, it's a key, a constant that unlocks the structure of reality. It tells us that time bends, space contracts, mass and energy are one. It isolates us in the cosmos, limiting how far we can reach and how fast we can communicate. It defines causality, ensuring that causes precede effects, that information doesn't travel backward in time, that the universe remains logically coherent, and it reveals that the universe is stranger, more flexible, more interconnected than we ever imagined. 299,792 kilometers per second. Always. Everywhere. For everyone. Not because it's the fastest speed we've measured, but because it's the fastest speed reality allows.